In this video we are going to analyze how to combine capacitors. We know that we already know that a capacitor is the set of two metallic two metallic surface that equal two metallic piece of surface that we put charge, but the charge will live in the exterior of the surface, so the electrical field will be zero here, and we put the same amount of positive charge in one surface and the same amount of negative charge in the other surface. This is a capacitor. We establish an electrical field and we create a difference in potential. The difference in potential is minus E scalar ddl. So V sub A, for any point AV, whatever you choose, any point AV, the difference in potential is the same one. Oh, why? Because the surface is an equipotential surface. If you take your point A here and your point V here, the difference in potential will be the same. V sub V minus V sub A will be a constant V0 for any 2 points of the surface. And this is very important to take into account. And this is due because the surface of an electrical conductor is an equipotential surface. So in this video, what we are going to study is what happens if we make arrangement of capacitors in series and parallel. If we make it in series, you have two capacitors. This is positive charge. This is the first capacitor, C1. You connect the capacitor in series. What it means that you connect it in series? One after the other, one, okay. If you connect the other capacitor here, minus, but maybe you put more charge here. Okay, maybe the distance D2 here is different than D1. That's why here is C1 and here is C2. Maybe the area A2 is different. That is why C2 is different than C1. Okay, and you place another, and you charge, and you make an arrangement. So the problem here is like this. Okay, if you make this arrangement, what it will happen here is, let's say this is an insulator, the charge will not escape. What will happen here is that we have a problem. We need to connect these 2 points first. We need to connect these 2 points with a cable. So the cable will rearrange the charge, and at the end will appear, let me see if we can do it. Yes, we can do it. It will appear some charge Q1 here. The same charge minus Q1 here. The same charge plus Q1 here. And the same charge minus Q1 here. And now I can close the circuit. And now I have two capacitors. This one with capacitance C1 and this one with capacitance C2. Of course, the area of this one is A1. The area of these two is A2. The distance D1 is the distance separate the plates, and of course, because there is Q1 here and minus Q1 in the other plate, there is a difference in potential, delta V1 here, and here there is a difference in potential, delta V2. So we want to find the equivalent capacitance. What it means, the C equivalence, is the capacitor that we have to install in the middle of the system that will work in the same way. So the capacitor that we have to install here is a capacitor that will have the charge Q1 I don't know the distance. If it's d1 plus d2, I don't know what distance it will be. The charge minus q1 here. So this charge, I plot it here. And the potential will be v sub 1, v1 plus v2. Delta v1 plus delta v2. I call it v1 plus v2. So the C equivalent will be the capacitor that has the charge q1 when the two plates are at the potential delta v1 plus delta v2. Now, to relate this equation with the equations that C1 is Q1 divided by delta V1, and the equation that C2 is the same charge Q1 by divided by delta V2, to relate this equation, I cannot play with this equation. I have to play with the inverse, and the inverse of the equivalence will be delta V1 plus delta V2 divided by Q1. Okay, so 1 over C equivalent will be 1 over C1 plus 1 divided by C2. So I have proved you that the equivalence capacitance of an arrangement of two capacitors that are connected in series follow this rule. So if you have an example, one capacitor like this with 1 picofarad. Well, the capacitance is in farad, we know. 1 picofarad, okay, and so no one resistor. One capacitor of 1 picofarad, and you connect it in series with another capacitor of 2 picofarad. Here, between these 2 points, there are a difference in potential delta V1. Between these 2 points, there are a difference in potential delta V2. So the equivalent capacitor, C equivalent, it will be the capacitor that will have the charge plus Q here, minus Q here, the same charge that have this one, pure minus Q1, and the difference in potential will be delta V1 plus delta V2. So the equivalence capacitance will be C1 over C equivalent equal 1 divided by 1 plus 1 divided by 2, that is 2 divided by 2 plus 1 divided by 2 is 3 divided by 2. So C equivalent will be 2/3. As you see, the equivalent capacitance is smaller than C1 and smaller than C2. So this is the equivalent capacitance of a arrangement that is done with two capacitors that are arranged in a series. Let's go now to see in a parallel. For a parallel arrangement, we mean by a parallel arrangement an arrangement where the two capacitors are arranged in a way. You see, this is the one capacitor C1, this is the second capacitor C2, are arranged in a way that the difference in potential between the two plates of every capacitor is the same. The difference in potential between these plates and these plates is the same difference in potential, the difference in potential between these plates and this plate. Oh, so this is like a one metallic piece of material, of metallic piece. This is another metallic piece, this one with this one. So these have the charge Q1, these have the charge Q2. So the change in potential is the same one between these 2 points and between these 2 points, for example. Also between these 2 points and also between these 2 points, because all of them, they are equipotential surface. It's a metallic pieces, 2 metallic pieces that are at the same potential delta V. So the equivalence capacitance is what we are looking for. So the equivalent capacitance, C equivalence, will be the capacitor that have the charge Q at the potential delta V. What charge? The charge Q1 plus Q2, like here, you see Q1 plus Q2 in the potential delta V. But the potential delta V is the same one for both of them. So it will be C1 plus C2. Let's prove it. C equivalent is C1 plus C2. As an example, easy example, imagine that you install capacitors in parallel. Let's say like this, maybe like this. Yeah, why not? Like this. C1, C2, C3, C4. What is the equivalence capacitance? It's a capacitor that have what capacitance? Well, C equivalence is C1 plus C2 plus C3 plus C4. So, if this is 1 picofarad, 2 picofarad, 3 picofarad, 4 picofarad, C equivalence will be 1 plus 2 plus 3 plus 4 picofarad. 7, 8, 9, 10 picofarad. So this is the equivalence. So you place a C equivalent capacitor here that will have 10 picofarad and will work exactly in the same in the circuit exactly as is working the whole system of the 4 capacitors.